Hi guys, so in today's video, I'm going to be talking about the physics chapter laws of motion. Alright, we can start now. Okay, so what are the laws of motion? There are three laws of motion as said by Isaac Newton, and they are our first law is the law of inertia. Second law, which is the derivation of the formula force equals to mass into acceleration, and our third law, which is the most common, like a lot of people know about this law, is that um, every action has an equal and opposite reaction. So we're going to be covering all of these laws in detail. Before we start with the laws of motion, I would like to address another important topic, which are contact and non contact forces. Now, contact forces, as we can tell by the name, are the forces which, when applied on a body, are making physical contact with the body. So, let me just demonstrate this better. I'm making physical contact with the body. For example, we have frictional force, which is, I'll give an example of friction force here. This is frictional force. I'm not going to explain frictional force since that is a pretty basic topic, but that's an example of contact force. We have normal reaction force, which is again a contact force. Normal reaction force is basically when a body is placed on a surface, the body exerts a force downwards, correct, and equal to its weight. And on the surface of this body, but the body does not fall or move, correct. So, if I'll just explain this. So, if you have an box kept on a table, the box will not fall even though it's exerting force, a certain amount of force which equals to its weight on the table. So why does this happen? This happens because this surface, the one I'm shading right now, that basically the table which the box is kept on, exerts an equal force in the opposite direction. That's why the body stays on the table. So that's it about normal reaction force. There are other contact forces like tension force as applied through strings. Then there is tension force, there's force exerted by spring, and yeah, that's, and there's also muscular force, but that's about it. Of course, there are many more which I have not covered, but this is, I'm not going to go into detail on contact and non-contact forces. They're just important. Some of the non-contact forces are gravitational force. Gravitational force. These are the non-contact forces. So they do not require contact with the body to exert force. So there's gravitational force. There is electrostatic force, which you can see by a common experiment of rubbing the comb on your hair and then putting it above bits of paper, and they will get attracted towards the comb. Yeah, that's example of electrostatic force. And then there's also magnetic force, which is again very common and known by a lot of people. Okay, so that's it about contact and non-contact forces. Contact forces are forces which require contact to exert a certain force on the body, and non-contact is the opposite. They do not require contact to exert a force on the body. Now we're gonna go towards our first law of motion, which, as I mentioned before, is the law of inertia. What is the law of inertia? Law of inertia states that if a body is in a state of rest or it's in a state of motion, it will stay in its current state unless an external force is applied on the body which changes its state. For example, if you throw a ball on the ground, it will move a certain distance and then eventually stop. So this ball stops because there's an external force of friction acting upon the ball. If this friction was not present, the ball, according to the law, would move on forever. So I'm gonna repeat the law again. A bo- if a body is in a state of rest, it will remain in the state of rest, and if it is in the state of motion, it will remain in the state of motion in the same direction with the same speed unless an external force is acted upon it. External force is acted upon it. And that's our first law, the law of inertia. Alright, moving on. Our second law, also known as the law of F equals to ma. Okay, our second law states, according to Newton's second law, the rate of change of momentum of a body is directly proportional to the force on the body, and the change in momentum takes place in the same direction in which the force is applied. So before you understand this law, obviously you need to know what momentum is. So the product linear momentum, which is what we're talking about here. Linear momentum, we represent momentum by the letter P, is the product of the mass and velocity of the body. So momentum equals to m multiplied by v, or mv. The linear momentum, as I said, is denoted by the letter P, and the expression which we use to find momentum is P equals to mv. Alright. So as we know, the change in any value is represented by the Greek symbol delta. So the change in momentum would be equal to delta m delta v, or delta mv. Correct. So there is a derivation, and this derivation says that the change in momentum over the change in momentum over a certain period of time equals to the change in the final mass and velocity of the body minus the initial mass and velocity of the body. What does this mean? Supposing that the mass of the body is constant, suppose you have a mass 50 kg and it's constant, the mass for the body is constant, and the velocity of the body changing from 20 to say 30. So the change in momentum would be equal to mv, that means m times the final velocity minus m times the initial velocity divided by time. Now over here final velocity is 30 and initial velocity is 20, and suppose the time taken is 5 and you multiply both of these by 50. 50 times 30 is 1500 minus 20 times 50 is 1000, divide by 5, which equals to 500 over 5, which equals to 100. So we can say that the change in momentum of the body equals to 100. So the proper derivation for this is delta p, or change in momentum over a certain period of time, directly proportional to mv minus mu divided by t. So over here we can take m common, so therefore delta p over t is directly proportional to m v minus u divided by t, since m is just constant and it's common in these two. So if we take m here, v minus u over t is just the formula for acceleration. Therefore we can say delta p over t is directly proportional to acceleration. Oh sorry, is directly proportional to ma. Alright, if we add a constant, we can say that this delta p over t, which is basically a force, is directly proportional to ma. So if f is directly proportional to ma, we can take all of the values as 1, acceleration 1, mass of the body 1, and force 1. So if we take 1 constant, we can add say k as a constant, and of course you must have learned in maths, to remove the proportion sign you add a constant value. So same way over here we add k, which equals to 1 as a constant. To remove the proportion sign, make it equal to, therefore f equals to kma. Since since k is just 1, we can rewrite this as f equal to ma, and that's how we derive it. That's the entire history behind this derivation. So change in momentum over time is equal to m bracket v minus u over t, and from that equation we derive f equals to ma. Fascinating. And that is the second law. I'll just repeat the words of the second law. According to Newton's second law, the change in momentum, that means this, is directly proportional to the force applied on it, and the change in momentum takes place in the direction in which the force is there, in the same direction as the force which is applied on the body. So if the force applied on the body is in this direction, the change in momentum will also take place in this direction, and that's Newton's second law. Newton's third law, as I said before, is I'll say it properly. To every action there is a equal and opposite reaction. To every action there is an equal and opposite reaction. So this would mean that an interaction of two bodies A and B, the magnitude of the reaction, which is, so we have one body A and one body B. Alright, so these both interact. This interaction create a certain force of magnitude. Suppose this is force AB. So the force applied by A would be force FA, and the force applied by B would be FB, and the total magnitude of the reaction would be FAB. So in interaction of two bodies A and B, the magnitude of reaction, that is the force AB applied by the body B on body A, is equal in magnitude to the action force BA applied on body A by body B, but they are in directions opposite to each other. Alright, I'll demonstrate this better. If you have an object A, an object B, and B is applying a certain force on A, and suppose the magnitude of this force is AB, and then you have an object A here and then B, and A is applying a certain force on B, and this equals to FBA. So according to Newton's third law, FAB would be equal to FBA. That is basically it for Newton's third law of motion. Of course, when you're learning laws of motion, it is important to learn gravitation and free fall. So I'm going to cover those topics here. Now, what is gravity? Gravity is a force that attracts bodies towards each other due to their masses. That's basically what gravity is. So you might have learned gravity before, so I'm not gonna put too much detail on it. I'm gonna go ahead and tell you the universal law of gravitation. So the universal law of gravitation states that F is equals to G m1 m2 divided by r squared. What does this mean? Over here, F is force. This G, it's known as the gravitational constant, which Newton had derived. And m1 is the mass of body 1, so mass 1. M2 is the mass of body 2, so mass 2. R squared is the distance between the two bodies squared. So I'll give an example. So if you want to calculate the gravitational force between two bodies of mass 2 kg and mass say 3 kg with the distance between them as 2, so how would you do this? This would be, therefore the force would be equal to the gravitational constant times 2 times 3 divided by the distance between them squared, so that's 2 squared 4. Okay, so to solve this equation, the gravitational constant is valued at 6.67 multiplied by 10 raised to minus 11, and the unit for this is Newton meter square per kilogram square. So how did you get this? So from F equals to G m1 m2 over r squared, we can get the value of G, which would be equal to Newton times meter square divided by kg times kg. So the unit would just become Newton meter square per kilogram square, or as I wrote it before, nm squared per kg raised to minus 2. That's the unit for the gravitational constant. So this question we were doing before, when you plug in this value, you will and you do this, so you can reduce this to 1, and whatever this value is multiplied by 3 divided by 2, and you will get the resultant force, whatever it is. That's how you calculate the force of gravity between two objects. So you have to remember the gravitational constant and the acceleration due to gravity, g, are two different things. The gravitational constant was derived by Newton, not only considering the earth. It was, he calculated it by the finding out the force of 1 newton multiplied by 1 meter square divided by 1 kilogram times 1 kilogram. That's how he derived the gravitational constant. Acceleration due to gravity, which is just for earth, by the way, the 9.8 value, was derived as an acceleration due to gravity. So g is not gravity. G, small g, is an acceleration caused due to gravity. Caused due to gravity. So g is not gravity, and it is definitely different from the gravitational constant. G is just an acceleration caused by gravity. We like to call it acceleration due to gravity. Alright, so you might be wondering how we got the value g. So I'm gonna tell you that. So we know that F equals to g m1 m2 divided by r squared. We also know F equals to ma, which is acceleration. So on earth, a we like to call g, which is acceleration due to gravity. So we can rewrite this as mg equals to m1 m2 over r squared. So we can cancel over here. This m is the mass of the body, mass of any body on earth, any body on earth, and this m is the mass of the earth, and this r squared is the radius of the earth squared. So when you cancel all we're left with is g equals to the mass of the earth times the gravitational constant divided by the square of the radius of the earth. And when you plug in all these values, this would be equal to 9.8 meter per second squared. That is the acceleration caused due to the non-contact force gravity on our planet Earth. And of course 9.8 would not be the case for all planets, because the mass of every celestial body is different, including Earth. And yeah, that's it for